Hey everyone, it's Alex again, and today we're going over a pretty important lesson, resistive circuits. So this is all going to be about resistors and their different kinds of configurations. So first of all, we're going to talk about the series configuration, which I'm sure that you guys are all familiar with. Basically, what it is just a string of resistors connected from. We have this point right here is directly connected to the next resistor, is directly connected to the next resistor. And so a common example would be like those Christmas lights where if one of the bulbs or the resistors goes out, then the whole circuit dies, right? Everything else, because the circuit is broken, no current can flow through. So mathematically, it's represented as the sum of the R of the resistors in the series is equal to R equivalent, okay, which is the total resistance as seen by the power source. Or R1 plus R2 plus dot 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 plus RI. Here are some properties that are just nice to know in a pinch. So properties: current is the same throughout, but the voltage drops. So right here we have one voltage 1. So say that the total voltage is V, right? Then all of these guys added up together, V1, V2, V3, is supposed to equal the voltage drop down the circuit. And so each one of these resistors contributes to a voltage drop, right? Here's a little diagram of 3 light bulbs that I drew. Say that the power source is right here, right? Just some 9-volt battery, and then it's obviously connected it over this way like that. The light bulb that is closest to this battery is going to receive the most amount of voltage. Then it's going to drop it through here. There's going to be a voltage drop through here, and the next light bulb is going to get that much voltage left from the voltage drop, and then the last light bulb gets the least amount. So that's series. Now parallel. So parallel is going to be each one of the resistors are going to be set up in parallel, so a node connects all of the resistors first part, right, the first part of the resistor, and all of the last part of the resistor. So this is a node, this is a node, they are in parallel. And we have right here the mathematical version of it. The sum of the inverses of each resistor is equal to the inverse of R equivalent. And I have this note right here. It's very interesting to note also that a lot of people forget about this, and a lot of people get a lot of problems wrong like this. This right here is not R equivalent, okay? But it is the inverse of it. So you are going to have to flip this guy around on your calculator to ensure that you get the right answer. So just remember that. Yeah, and this expanded is just going to be 1 over R1 plus 1 over R2 plus dot 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 plus 1 over Ri. Okay. We're going to go over this cheap trick after I show you this diagram of what I was saying. So here, the voltage is the same across, so each one gets the same amount of voltage, but the current is divided amongst them, which we will talk about a little more in detail in a different lesson. But each one will get the same amount of energy or the same amount of voltage drop. So the voltage right here, say that we have a battery producing the 9 volts. Plus minus, that's not right, but right here we have ground, 0 volts. So the entirety of this has a voltage drop of 9 volts. Each one of these guys has a voltage drop of 9 volts, right? And depending on the resistive load, how much the resistance each one carries will determine how much current actually goes through each one. Okay, so the cheap trick. So when you have two resistors in R1 and R2, you can do this right here. And I will prove that to you guys. So we have 1 over R equivalent is equal to 1 over R1 plus 1 over R2, right? And now we want to combine these guys. Okay, so how are we going to combine them? Well, we're going to multiply by a factor of 1 for both sides so that we get a common denominator. We get R2 over R1, R2, because I multiplied this guy by R2 over R2. And then I multiply this guy by R1 over R1. Does not change the equation because those are just factors of 1. And we get plus R1 over R1, R2. And so we get R1 plus R2 over R1, R2. Now remember, this right here, that's still our 1 over R equivalent. So we have to flip it. So we're going to get R1, R2 over R1 plus R2. So that's cheap trick number 1. And very useful if, very, very useful. Oh, and here are the properties, which I described earlier. I actually should have put this above this, but it is what it is. So the properties of a parallel circuit, we got the voltage is the same among the nodes, but the current is split among the branches, which is dependent on the amount of the magnitude of resistance of each load. And here's a second cheap trick, which is super useful if R1 and R2 are the same. So if this guy and this guy are the same amount of resistance, then R equivalent is simply just R over 2. And once again, this is a very, very easy proof. All you have to do is say that R1 equals R2, and we're going to give it a new name. We're just going to give it R, and so it's going to be 1 over R plus 1 over R, and we get 2 over R. But remember, this is 1 over REQ, R equivalent. So flipping it, we get R equivalent equals R over 2. And so that's cheap trick number 2. Now, we have to be careful because we're in circuit analysis now. All of this is probably stuff you've known from E&M, and there are gonna be problems where we cannot solve for the series or the parallel because the resistors are not in series and parallel. So note number 1 is to be careful. Be careful about the nodes. So right here, it was very obvious that we had the first part of this resistor and the first part of this resistor connected by a single node, and then the last part of this resistor, etc., connected by this node right here. However, you're going to get cases like this. So notice right here, let's look simply at, well, I guess I already have it written down here. Let's look at this right here. We say that this resistor right here is, let's say a student says, oh, if this is parallel. Well, they are right for this part. This part begins as being, parallel. But then right here, we see that these are two different nodes, right? And so this circuit is neither series nor parallel. And unless we take this off, unless this is gone and this is gone, then we can say these two are in parallel. and I mean are in series. These two are in series, and then the whole configuration is in parallel. However, this is not the case. We're saying that this is part of some other system, right? System. Okay. So you can't do anything there until we learn some new methods in the next few lessons. So that is a very brief overview of series and parallel circuits. We're going to do a few example problems in the next lesson, and then we're going to move on to two important case-based scenario tools, and then we're going to get into the really powerful stuff for this unit. So hope you enjoyed, and see you later.